convolutional neural network for NLP. So it's totally like a new kind of neural network we never actually tried it before. It's kind of different from the RNN, the recurrent neural network we talked about. So there's 3 different parts of today's lecture. The first part will be the introduction of the CNN and some kind of like simple architecture of the CNN neural network. And the second part is some kind of general introduction to some complicated or complex CNNs or some kind of frontier research on the convolutional neural network. And last part, I'll show you a notebook, which I wrote it myself. It's kind of like a really simple, like empirical introduction to show you guys how to actually write a Python code or using TensorFlow 2.0 to actually construct your own convolutional neural network on the CIFAR, which is like a really famous, like colorful picture kind of like data set, or which I'll show you later. So first part, introduction to CNN. The first kind of question I want to answer, or I want to actually answer for all of you, is like, what is CNN? So the core idea of the convolutional neural network is actually to compute vectors for every possible word sequences. Okay, so now we're talking about for natural language processing for this specific purpose. So basically, we loop through every single window or every single subsequences over there using a sliding window, which is very different from the previous like RNN before. For example, if we have the sentence like tentative deal reached to keep government open. Suppose we have this sentence right here. So the first kind of stage the convolutional neural network is gonna do is actually to parse this sentence into different parts. So suppose we're doing a subsequence of length 3. So suppose the length is 3. Then we are gonna do this 3 word first. We're gonna loops like the first loop is gonna be this 3 word. Second loop is gonna be this 3 word. And next 3 word is gonna be this 3 word. So we're kind of keep going. It's like very similar to the window classification we actually learned before. So basically we are sliding each kind of like a window, each window of length 3 from left to right. Then we got a different kind of vectors. And those vectors are actually the inputs we are going to use for the convolutional neural network. Okay, so we don't really care. So we don't really care whether the phrase, especially this part, is grammatical. We don't really care about the grammar. That's because we just like loop through every 3 words every single time we slide in the window to the right. So we don't really care about the grammar. In fact, this is not very linguistically and cognitively plausible. So basically, that means the task is a little bit different than RNN, because RNN focuses on grammatical or linguistic or cognitive like sentence, which totally makes sense. So we construct a sentence, using the previous word. So this sentence should actually make perfect sense, which when you read it, it should be grammatically right or linguistically right. But for this one, this is not our purpose. We don't construct a sentence which is grammatically right. So basically, we just try to extract every single subcomponent here, and we try to classify this whole sentence and see what is the semantic meaning of the sentence. So for example, these 3 words actually tell us a little bit about a deal. And this 3 word actually is still about the deal, right? And this 3 word is like, oh, the deal is reached. And next 3 word tells about a government, and next part is still government. So we cannot understand this whole sentence is about a deal that is about a government. So that's it. So basically, CNN is used to understand the semantic meaning of the sentence. It's not used to construct a perfect like sentence. So keep that in mind. So convolutional neural network is actually classically used to actual features, especially from images. Okay. Actually, before we start lecture, I had a conversation with Isa. We actually talked about this. So as you can see, if you go to the lecture notes, this kind of course doesn't actually spend a lot of time on CNN. Part of the reason is that CNN is not very commonly used for NLP like RNN. It's actually originated from the image classification task, which is very commonly used for image classification. Okay, so let's switch a little bit to the image. I just want to give you guys a little bit introduction on image and tells you guys what kind of like the classical convolutional neural network looks like for image classification. So there's three. So this is like CNN is a deep learning algorithm which takes input, which is image for image classification. Suppose we are looking for this, assign importance, learnable weights or bias to various like aspects, objects in the image, and be able to differentiate one from the other. So if you look at the last sentence here, basically this is image classification or face recognition. That's the purpose of CNN. So CNN has three main components. One is input image. Second is filter. This is super important, which is unique to CNN. And last part is output image. So for example, in the CNN looks like this. So we have the input image and we have the filter, which I'll explain later, what kind of stuff is the filter is. This is more like a pattern finder. So you can think about this as a weight W here. Think about this as an X. So basically we multiply W with X and we apply that, we plus a bias term, then we get a Y. Then we do some kind of nonlinear transformation. Suppose it's a softmax. So WX plus B, right? Then we got the output. Okay, so basically that's how the flow of the convolutional neural network works. So you can think about the filter as from two different perspectives. So first part you can think about is just a blur filter. That is, the CNN process can be thought of creating a blurred version of the input image, just like this. So basically, we apply this filter to every single pixel. And at the end, we got this. Or, it's kind of like we reprocess the image a little bit. Or you can think about it as edge detection. So as the input, we have the original image. As the output, we have the white lines as the edge, while black as those without edge. So if you think of the filter as edge detection, so basically this filter here try to find whether there's an edge of the person here. So if there's no edge of the person, then it's gonna be black. If I go here, the filter times this kind of specific pixel, oh, I find the edge. So here, there's the edge. Okay, so basically you can think about the filter as a pattern finder. So what kind of like a pattern do you looking for? Are you looking for? It depends on you. So you can design your like a filter yourself. So your filter can be edge detector, can be color detector, can be a blur detector. So it all depends on your kind of task over there. Okay. So from this perspective, you can think about saying as a model of image modifier. So with output image as a modified version of the input image here. Okay, so each filter is a W here. So each filter specifies a specific feature of the image, which is kind of related to the image. So as you can remember before, we actually multiplied image with a filter. So when you multiply W with X, so basically what you are doing is you are seeing the cosine similarity between W and X. Okay, so you try to say, oh, is this pixel similar to this edge, or is this picture or this pixel similar to the edge? So basically, you by multiplying them, you try to see whether there's a correlation between or the similarity between each pixel and the weight here. Okay, so what makes the thing work? What actually differentiate one thing from the other is actually the filter. So this is specifically designed for CNN. If we actually use a a different kind of filter, we'll have a different kind of image. So if we use a Gaussian filter, you will have a blurred image. If we have the edge detection filter, we'll have the edge image, just like I mentioned before. So you can have your own kind of filter, which specifically designed for your own kind of like telescope there. Okay. So now let's go to a little bit more detail about the filter, the mechanics of the convolution. So we have 3 key factors, which is the input, filter, and output. So to actually dominate the process, suppose we have the following input, filter, and output in the matrix form. So suppose this is the image, okay? So usually the image is in pixel unit, and each pixel can be think about as a sub matrix over here, okay? Suppose this is the image, this is the filter, this is the output. So what does the filter do? So filter basically does this. So suppose this filter is 2 by 2, and this is 4 by 4 image. Okay. So the filter, what the filter does is, I'm gonna go find this corner first. Okay, and multiply each number. Okay, each number element wise, and sum them up. I got my output here, 60. Okay, 60. Okay, and next part, I'm gonna slide this kind of filter to the right by 1 unit, by 1 column. Then I do the same, element-wise product, and sum them up, 70. Okay, so what does that mean? So basically stop here, that means, oh, the first pixel is not quite similar to the filter. So the first pixel is similarity between the first pixel and the filter is only 60. But between the second kind of pixel is 70. So basically that means, oh, this actually means we are getting closer to the filter or the output we want. Suppose this is, we try to find the red color. Basically that means you have 60%, which is not very precise, but you can think about it this way. 60% of the chance you can find a red color here, but here you have 70% of a chance. So basically that means this is more like a red color than this one, okay? So we keep doing that, try to slide every single row, every single column. So we got this, and we keep going until we have we actually looped through every single, sub matrix, just like before, okay? So at the end, we get this output. So that's our first stage. So this is called a convolution output. Okay, convolution output. So basically there's a theory. So if the length of the input is n, which is 4 here, okay, 4 here, and the kernel, so filter is also called a kernel, okay? So there are 2 kind of names for it. You can call it kernel, you can call it filter. If the kernel length is also k, which is 2 here, okay, 4 and 2 here. Then the output length, if you don't do any specific padding, which we'll talk about later, will be 4 minus 2 plus 1, which is 3. Okay, which is 3 here. Okay. So let's pause here for a second. Try to make sure every single one of us understand what filter actually, what a filter actually can do for CNN here. Any question here?
So Daniel, so in NLP, do we use 1D filter only?
Yes, actually, which I'm going to talk about later. So in NLP, we'll actually use 1D filter, but in image, we use actually 2D or even more 3D filter. Yeah. Yeah, that's a very good question. I will talk about that later for sure. Yeah.
Okay, thank you.
So here is a 2, because the image is usually like one image is 2D. So here, the filter should also be 2D. So no question, let's keep going, okay? So first kind of like, there's some kind of specific details I want to actually go through here. So basically we actually went through that part. So yeah, so just like I said, a filter is actually a pattern finder. So you can think about this as input image. Think about this as a filter. So basically, we loop through every single pixel of the image. We try to find the left eye here. Okay. So right here, you should get a 100%, or which is a very high number than any other, pixel on the image. Okay, so in that way, we actually find this kind of eye over here. So we can actually use that for next step, which we'll talk about later, to classify, oh, this is a girl. Okay, this is girl. Okay, so that's basically pattern finder. So yeah, basically filter you can find the left eyes in this position here. So in NLP, it's kind of similar. In NLP, it's kind of similar, but a little bit different for the terms and dimensionality analysis. So for example, suppose we have this sentence we talked about previously. Tentative deal reached to keep government open. So this is actually 1D. This is actually 1D, not 2D, because we only have one sentence, which is a sequence here, right? So basically, we only have one line of the words. So basically, we have 1, 2, 3, 7 words, and each word we give it a dimension. We actually use, an embedding to represent it, which is 4. The embedding size is 4. So this matrix is 7 times 4. So that's the input. So suppose we have the filter. We have the filter size 3 here. It's also 1D, but we actually give it in, kind of dimension to make it a matrix. So suppose the filter size is 3. So the 3 refers to the number of the rows. Okay. So if we actually apply the filter to the sentence here, so basically what we do here is we are going to loop through, we are going to move the window here. That's the first step. Second step, next step. So every single time when I actually, fix the size or the position of the window, I'm going to multiply each component here element-wise, just like before, and sum them up. We got the output here. Okay, we got an output here. So this first kind of like output here actually represents 3 words: tentative, deal, and reach. Right? Does that make sense? Right? So the second one is going to be this. It's going to be deal, reach 2. So element-wise products and sum them up is going to be this number here, okay? So basically, what this output is saying is that, oh, KGO is very similar, or keep government open is very similar to the filter. So maybe this filter specializes in finding government. Okay, so that's why this got the highest number here, okay? And other kind of like subcomponents or phrases, it doesn't have that high number over there. Okay. So basically, we try to break a sentence into different parts. We classify each subpart. Then we add all the classified subparts. Just actually classifies the whole sentence right here. Okay. So again, if the input length is n, the filter size is k, then the output size should be n minus k plus 1. So it's gonna be 7 here minus 3. Plus 1, which is 5. Okay. So this is actually without any padding, and I want to introduce a little bit more term here. So each column here in the input, or in the filter or kernel, or in the output is called channel. Okay, it's called a channel. So this one's called a channel. That's the third channel, second channel, first channel. Okay, that's called a channel. Okay, and each filter can be considered as a weight. So like I said, this is weight, this is X. That actually specialize in different semantic patterns. So that's what I talked about previously. This basically specializes in government. So that's kind of specific pattern I try to find here. Okay, so another concept I want to introduce a little bit here is called padding. Okay, it's called padding. So the movement of the filter is actually bounded by the edges, right? So basically, when you move that, you have to, it's bounded by the edge here. So the output is always smaller than the input. As you can see, that's 7 times 4, and here's like 5 times 1, right? It's always smaller than the original output. So what if we want the output image to be the same size as input image, which makes more convenient when we actually transfer the output to the next layer? Okay, what if we try to do that? So that for that kind of purpose, we need padding. We need some padding. So basically, we need to add some imaginary zeros around the input, basically here. For example, this is original matrix here. This is without padding. So suppose I want to actually construct an output which has the same size of the input. So what we do here is we are going to do a little bit of padding here for all kind of the edges here. And every single component here is zero. So in that way, we keep doing the same. We loop through the same kind of window here. So every single time we just select a 3 and 3, right? So in that way, we can actually construct the same output as before. So another kind of like so that is called, so in the TensorFlow 2.0, this is called same padding mode, okay? And the original one without any padding is called a valid mode. So for the valid mode, the output size is going to be n minus k plus 1, and for the same mode, it's going to be the same as the input. And those two are very typical. Okay, actually, this one's very commonly used, most commonly used right here. Okay, what is the full padding? So this is not a typical kind of like used padding for most of the time. So basically, that means I just want the output size to be larger than the input size. I want a bigger output. Which is not recommended because for image classification, as I'll show you later, we try to compress the image as smaller across as we proceeding to the first more kind of like layers over there. So, but still, like, what is the full padding? Full padding basically means we're gonna pad a little bit more than just like 1 or 2 lines or actually column zeros, so that when we do the pattern sliding window here, we can actually find a larger output than before. So for this one, it's called full padding, and the output size is going to be n plus k minus 1. And this is not typical. At least I didn't actually use that. I actually never tried that before. I just use those two very commonly here. Okay. So that's a padding. Any question with respect to the padding?
Daniel, I just wondering, like, for the weights you mentioned, why don't we use the dot product and instead of the element-wise multiplying? So when do we choose to use which one in this case?
Okay. So basically, we don't actually use the product is because sometimes when you do a filter, the filter size may not match with the input size. For example, this one has 4 by 3, right? 4 by 3 here. And this one is 3 by 4, right? If you do that, if you do actually do the matrix multiplication, it's going to be 4 by 3, 3 by 4. It's going to be 4 by 4. It's going to be 4 by 4 matrix. Then that makes sense,
Okay,
right?
cool.
So yeah. So if we actually transpose a little bit to match the the dimension over there, because if you look at this one, this is actually 1, 2, 3, 3 times 4, and this is also 3 times 4. So what I understand is like you cannot actually multiply them together because sometimes when your filter size doesn't really match your your actually the original kind of like matrix size here, especially this one is 7 over times 4 here, right? So I guess your question is like, why not just multiply the whole kind of like matrix or the image with this one here? Is that your question?
I mean, it sort of like answered my question. I just wonder, like, you were saying dot product. So is there any situation that we use dot product in this case?
No,
maybe
actually we don't. So as you can see here, the output size is actually only 1 column, right? So basically the pattern has another purpose, that is we try to compress the image into a smaller image, right? So this is a huge image and we compress into a smaller image. If we use a dot product, it's still going to be a matrix. It's not going to be a vector anymore. So you're not actually compressing the image size. So, and in that way, that's actually basically not CNN is going to work. So actually CNN is going to do element-wise product, not actually just the matrix multiplication actually.
Cool, that makes sense. Thanks.
Yeah. So I guess we can jump forward a little bit. Let me show you the image. Yeah. So basically, think about this as input at the first layer, right? So we try to find a pattern here, right? And after we find the pattern here, we actually compress into a smaller image. And then we can keep going and find another kind of pattern in the second layer. And after we do that, it's going to be compressed a little bit more. Now we have 8 times 8 image, but this pattern, this kind of filter maybe is still the same size. That means we can capture more information with smaller size image. At the end, we have 4 by 4, and suppose the filter size is like 3. Now we can capture most of the image information. That's basically, how CNN is gonna work. But if you do the, matrix sum multiplication, it probably gonna get bigger and bigger, right? And if you use the same filter size, it's not gonna work. It's actually gonna capture less and less information as you're proceeding. Does that make sense? I guess, that's what we are gonna talk about later, but let's jump forward to that part a little bit, yes. Did I answer your question from that perspective? Yeah. Okay.
Thanks.
Yeah. So yeah, basically that's how the pattern, the padding is gonna work. So okay, now that's for the image. How does the padding is gonna work for the sentence here? So basically, because we only have 1D, right? So basically, you only have to pad on the top and pad on the bottom here. So if you just pad it with 2 rows here, as you can see, it's going to be 9/4, right? And if you keep going now using the same kind of filter, now we have 3 filters. Filter 1, 2, 3. Previously, we only have this one filter. We don't have those 2 filters. So we only have 1 column here, right? So 9 minus 3 plus 1 is going to be 7. So now we have 7 rows here, which is exactly the same kind of size as input image. But also we have 2 more filters here. So we are going to have 1, 2, 3 channel. Okay, 2 more columns as before. So as I mentioned previously, you can think about each filter as specific language or semantic pattern. So this one maybe it's about, a political stuff. And this one maybe is about food. And this one maybe is about, I don't know, government here, right? So each kind of like channel here specify a specific, sub semantic meaning of the sentence here. So this one is about political, and this one about food, and this one's about, government here. So basically, they actually have different roles to play and try to classify each subcomponent here, okay, by looping through every single sentence of here, okay. So that's how it's gonna work. The padding is gonna work for feature map. So this is the same padding. So this mode is the same. Okay, and previously we don't actually add 0. That's called a valid padding. Okay. Okay, another concept is called feature map. So the output activations for a given filter will be called feature maps or activation maps. So basically, once you finish every single step right here, so we have the W here, we have the X, and we probably gonna have a bias term, and this is the output. So we are gonna use a nonlinear function here to process the output, okay? And the dimension, or especially the last dimension of this nonlinear transformation with output or activation is called feature maps. And for this one, suppose the nonlinear transformation of this one should be, I guess should be 7. Okay, so the output or the feature maps, output maps or feature maps is going to be 7 in this case. Okay, so again, the output activations for a given filter will be called feature maps, and the size of the final dimension refer to the number of the channels. Okay, so the nonlinear transformation with this is called feature maps, and these are just different channels or different kind of like a feature maps, 3 feature maps here. Okay. Okay. So that's a feature map. So what does a convolutional layer look like? It's gonna be like this actually, just like I mentioned previously. We actually use the filter times the input plus a bias term, then we do a nonlinear transformation on top of that. Okay. Okay. So that's a feature map. We talk about the polling here. Okay, we talked about the padding. Now let's talk about the polling here. Okay, that's another concept right here. So we basically have the two different stages for seeing in. Okay, so the first stage is going to be a series of convolutional layers followed by polling layers. So this is one type of stage one. So basically, it's going to look like this. We do a convolution just like this one. So this whole part here is actually a convolutional layer. So we do a convolutional layer, then we do a polling, then we do another convolutional layer, and we do another polling, so on and so forth. So I'm going to explain what a polling is later, but now let's take my word. This is stage one. And stage two is after we finish the stage one, we're going to concate every single input here or output from this kind of first stage into a dense layer. And we're going to use the softmax function or a ReLU function or a nonlinear transformation to classify the output from this. Okay, so what is polling in stage one? At a higher level, polling is actually a downstamp polling. Specifically, it's actually outputs a smaller image or smaller sentence from a bigger image or actually bigger kind of like sentence over there. So there are two types of pollings. So now this polling here is for image classification. For NLP, it has different terms. So for image is actually called polling, and for NLP, which I'll talk about later, is called polling over time. Okay, so for the image classification, we have two kinds of pollings: max polling or average polling. So it's very simple. Max polling, basically, you take the max of each sub matrix here. So suppose we have, this size of 2, the polling or the filter size of 2. So, or polling size of 2 actually. So more specifically, it's going to be the polling size here is going to be 2 by 2 matrix here because it's 2D convolution here. So we loop through every single sub matrix here, right? So it's going to be 1, 2, 5, 6, and we find the largest one of each sub matrix, which is 6. And this one's going to be 8, 16, and 14. Okay. So this is polling is not kernel. Okay, it doesn't equal to kernel. It doesn't equal to kernel. It doesn't equal to filter. It's just another way of compressing the image. That is, after we find the kernel, we are going to do split them into different kind of like a sub matrix here and try to find the max number over there. That's max polling. Average polling is very simple. You just take the same kind of sub matrix and you take the average of the 4 number here. Okay, that's how you got the average polling over there. Average polling over there. Okay, so that's for an image. How does polling look like for an NLP here? Okay, for NLP, it's called polling over time. Polling over time. It takes 1D feature vector and compare and compute the max or the average, which is actually already applied in NLP here. Okay, so local max polling over time. Local max polling over time, or max polling over time. Sometimes when we talk about max polling over time, you already refer to local. Okay, so what the local mean basically is we finish the first step by actually apply all the filter to all the subcomponents here. Okay, so this is the same kind of table as we do before after kernel or filter. Okay, so polling, what polling is going to do is I'm going to find the max number of each channel. 0.3 here, 1.6, 1.4. So I compress each convolutional layer from, suppose 1, 2, 3, 4, 7, 7 times 3 matrix into 1 times 3 matrix, 1 times 3 matrix. That is, I try to find the most specific pattern across each channel here. Since this one's about political, I just find the words that are most correlated to political, which is these 3 words here. Okay, and this one's about food. So I'm gonna find the three words and the most correlated to food, which is this 3 here, 1.4. And this is very, very commonly used. Actually, most of the time, people actually use max polling and it behaves normally well compared with other polling kind of skills over there. Okay, because when we try to classify a sentence, we try to find the most attractive or the core idea or the specific keywords of the sentence. Think about the way when you use an IELTS test or some kind of reading test, you don't actually memorize the whole sentence. You memorize the specific keywords. So max pooling basically extracts the keywords for you by finding the most correlated words to each specific pattern here, okay? And average pooling. So what does average pooling do? So average pooling is actually a little bit different than that. Is after you have this kind of like, after the filter or after kernel size, we have the output, we're gonna average across all the kernels here, okay? So basically now I don't actually care about the keywords. I care about more kind of like, you know, the entire sentence a little bit more than just finding the keywords, because I care about each single word and want to average them out, okay? So this is gonna be the average pooling, okay? So basically it's another way after the kernel to compress the image or the sentence like a little bit more than before, okay? So why do we actually use a pooling? So practically, if we actually downsize the image or the sentence here, we have less data to process. And another kind of intuition is, you know, for the image classification or the text classification, I don't really care where in the image the feature occur or show up. I don't really care where the keywords in the sentence show up. I just care about it actually does. It showed up in the sentence or in the image. Suppose I try to find a political pattern here. I don't really care whether it showed up in the first position, second position, or third position. I just care about if it does show up right here. That's enough. Because I just trying to find whether it actually is in the sentence or not. So if that's our purpose, then pooling actually does that for us, okay? So our task is actually recognize the image or the sentence. So even the image or sentence is smaller, as long as we can actually recognize it, we can actually identify the sentence, that's fine, okay? So any question with the pooling? No question? Okay, let's proceed. Speaking of the pooling, many people could have some kind of questions about the pool size. So until now, we actually show the example of the pool size equal to 2. But however, we could have a non-square window or non-square kind of pool here. So we could have, you know, a pool size which is 2 by 3 or 3 by 2. But it's very uncommon. Most of the time, we'll have a square pool size or a square pool over there, which is the same kind of dimension for the width and length. Okay, so for the unsquare one, which is very unconventional, just keep that in mind, because by default, actually we use like a square pool way more often than unsquare pool there. Okay, so it's also possible for the pool boxes or the pool kind of like, yeah, pool boxes to overlap. So previously when we talk about this case, there's no overlap because we move by 2 steps, right? We move from here to here. That's a 2-step. But we could have moved by 1 step. In that way, we move from here to here so that, you know, those 2 boxes could overlap, just like this part here. Okay, so that actually introduced another kind of concept we're going to talk about later, which is the stride. But before that, let's talk about the pooling, intuition behind the pooling. So why actually a convolutional, why do we actually do the kernel, then actually do the pooling? So the core idea is that after the convolution, the pool, the image shrinks or the sentence becomes shorter and the filter size actually generally stays the same or actually increase. So for example, think about this sentence we had before. Suppose this is the first layer. After the first layer, I'm going to do another convolution. Just, you know, ignore the pooling for a second. Let's think about the kernel. So after this layer, I'm going to do another convolution layer on top of this, right? So suppose the kernel size is still 3. Previously, for each kind of sub component, I can capture 3 words. But if I do another kernel size of 3 here, how many words can I capture now? For the first layer, we can capture 3 words. But if we keep the same kind of filter, how many words can we capture each time? Any thoughts on this? If we do another convolution layer on top of this, and we keep the same kind of filter, how many words can we capture for each step?
Only one more?
No, 9 words actually. So if you do this, 1, 2, 3, 4, 5, 6. See? If you do this, another 9 words. If you do the next one, another 9 words. So basically, although you are compress the sentence into a smaller size, but you are capturing more and more words. And like as long as you keep the filter size the same. Does that make sense? Okay, so basically you slide the same kind of window. You take that as a new input, just like this. And you're gonna, like do this window, that window, and you have actually 9 words captured each. And if we do a little bit more, it's gonna actually multiply by 3. It's gonna be 12 words or 15 words, even a little bit more. Okay, so that's why this is working. We're actually, shrinking the image or the sentence by convolution or by polling or by kernel. But as long as the kernel size is the same, or as long as we increase the kernel size or increase the feature maps, we can capture more and more information as we're proceeding from the initial layer to the last layer. Okay. Does that make sense? And a question with this part? Okay, so basically this is a hierarchical feature of the thing, and we first learn things quite small, but as we proceeding with more and more layer, we learn larger and larger patterns. Okay, that's actually the magical part or the beauty of the thing over here. Okay, but you may ask, well, what is, like, since we get a lot of information by capturing more and more information here, does that mean we don't have any loss, or we don't actually have a disadvantage with that? Of course, we have a disadvantage where we have some kind of shortcomings. As you compressing the image or the sentences here, we lose the information for sure. As we shrink an image, we actually lose in some kind of information over here, especially the spatial information, or especially where the words appear or where the pattern appear in the image. But however, just like we talked about before, as we reduce the image size, as long as the kernel size is the same, or as long as we increase the number of the feature maps or the kernels through the layers, we actually gonna find more and more patterns. So we gain information on what feature to find when we actually proceeding with more and more layers over there. So even though we lose some kind of information, as long as the information is about spatial, which is not relevant to our kind of objective, we don't really care. Okay. So basically, yeah, it's just like this graph. So basically, we have this kind of image or this kind of sentence here, and we compress that into a smaller, like cube. But we actually increase the feature maps. We increase the filter size, and we compress a little bit more. Oh, now we have a more kind of filter. And as the end, we're gonna have a really small image, but we have a huge number of the feature maps or huge number of filters capture 360 perspective of the image over here. Okay. So yes, that's a polling. I think this is the last concept right here. Yes, this is the last concept right here. Stride. This stride. Okay. So there's another way to actually compress the image alternative to polling. So you don't have to stick to polling. You can also do a stride. So what stride do is, for example, okay, let's look at this sentence right here. What stride do is, suppose a stride is 2. That is, we're gonna move the filter. We're gonna move the filter, which is 3, by 2 steps every single time. Which is, this is the first step. I think so. I think this is the first step, and we're gonna do this. We're gonna skip the first 2 words. We're gonna, so I'm gonna actually draw this a little bit more. So this is the first step. Previously, without a stride, we don't actually do this. But previously, without stride, we're gonna do this, right? We move by 1 step here. Okay. So what a stride does is it tells you how many steps you should move with the filter, or how many steps you should have between 2 filters. If a stride is 2, that means basically now I don't move by 1 step, I move by 2 steps. So the second step is going to be here. Third step is going to be here. This step is going to be here. So the distance between every 2 kind of filters is going to be 2. Okay. So more formal definition is, I think we have the formal definition right here. So, stride is, okay. Let's see, convolution is just multiply and add with striding window. Oh yeah, sorry, I think I made a mistake. I didn't actually give the formal definition. Yeah, but the formal definition should be the step you take with the filter, So previously, if we don't actually specify the stride, it's going to be default as 1, just like before. But if the stride is 2, you're going to move by 2 steps right here. Okay, so yeah, that's a stride here. So basically, that means we are going to skip 2 words once a time. So as we can see previously, the first step is going to be here. So we capture this word, that word, this word. And second step is going to be here, right? So we capture D, R, T, okay? And third step is going to be, I guess it should be here. Yes. So we capture T, K, and government right here. Okay. So basically we are skipping, 2 words once a time here. Okay. So that's a stride. Using a stride, as you can see, we can still compress the image or the sentence a little bit more, because now we only have 1, 2, 3, 4 rows compared with the 7 rows over there. Okay. So you can do pulling, you can do a stride. So those 2 actually achieve the same kind of purpose, just compress an image a little bit more. But stride does it in a more aggressive way. That is, I'm going to skipping the words and just jump into the next word. Okay. So in the image, it looks like in the image, actually, we also can do a stride, because most of the time, suppose we are starting at this time point, at this point here. We're starting at this point here. So suppose that's our first step. And we don't actually, the way we do stride is that we don't actually care about the pixel next to that. We're going to jump to next pixel. We're going to jump to this pixel with a stride. So that's going to be the first step. That's going to be a second step. And the way the reason why we do that, or the intuition behind that, or underlying intuition, that since this car is all red, if we just skip 1 pixel, it doesn't really hurt, because next pixel is still going to be a red, right? So suppose all the surrounding colors are red. So if we're skipping 1 or 2 kind of like pixels or 1 or 2 words, it doesn't really hurt, because it's always going to be the same. Okay, so that's the intuition between the stride, or why sometimes people actually use the stride a little bit more often than the polling over there. So yeah, recall the image is just the patches of the stuff. In the image of the red car, if we actually select 1 position, then the pixel next to it will be highly similar, which will be very similar to the red kind of point we have. Otherwise, it's not an image, right? Because the image is just a bunch of pixels that actually get together with similar colors or the channels over there. Okay, but the problem is, stride is actually less used in C and for NLP. We don't actually use stride that often compared with polling for NLP, and why? Actually, I just want to spark a little bit of discussion right here. And why do we actually use a stride, just like for the color or the car right here for the NLP? Any thoughts on this? Why don't we actually skip the word? Why skipping the words or using stride equal to 2 or 3 isn't that useful for the NLP?
I'm actually guessing that if you do not use stride, then it's possible that you can preserve the context information more rather than using a stride.
Perfect. Yes, that's the answer. Exactly. So, because when we read a sentence right here, we care about the context, right? So every single word is kind of linked to the previous word. Just like, so sorry, what's your name?
Xuan.
Yeah, just like Xuan mentioned over here. So every single word is kind of related to a previous word, right? So if you skip some of the words, what if the skipped words are the context for the next word, or it's a keyword you're going to find? So that word is going to be missing, right? Suppose you were doing a max pooling here, right? Suppose you were doing max pooling here. Suppose I don't have this one, I don't have that one, I don't have this one. That means I actually skip some of the key information, which could be possible. Like for example, I could actually skip this one here. In that way, I can't find the precise kind of position or precise pattern of this sub-sentence anymore. Okay, so yeah, just like Shan mentioned, we care about context in NLP, just not like image, because image doesn't really have a context. As long as you always surrounded by the same color, and we don't really care. But for NLP here, context matters. So we cannot actually just simply just skip the words just like before. Okay, does that make sense? Any question on that? Okay, so yeah, basically, yeah, that's the stride. That's what we talked about previously, just like this one here. Okay, just like this one here. Okay, so that's a stride equal to 2. So if we try to apply those two together, local max pooling and stride equal to 2, we can do that as well. So basically, you can apply those two at the same time, but we don't actually recommend it because, just like I mentioned previously, stride doesn't really actually work very well in the NLP sentence in the context with sentence with the context over there. Okay, so basically, first step is we do pooling and we get this kind of output here. Second, we're going to do a stride on that. We're going to do stride and stride and stride with output. So basically, it's move 2 step here, and we find the max kind of like numbers of every single kind of like a stride over here. So the max number between this one, that one should be this, and this is gonna be, this kind of stride here. Okay, you can combine those two together. So that's how it works. So basically, you do a pooling, then you do a stride combined with the local max pooling, then you can get this kind of compressed sentence over here. Okay. So I guess, yeah, just like I mentioned, that's the last concept over here. Okay. So there's also global max pooling, which I don't think we're going to use that in NLP, but if you're curious, you can just look into this concept yourself. I will upload my notes to the shared folder later after the lecture here. Okay. Okay. Yeah. So we have the max pooling, we have the average max pooling over time, but we can also have key max pooling as well. So this one is super simple, just like a max pooling. So suppose the key max pooling is 2, that means we're going to take the key maximums and throw out others instead of just taking the max number or from the input here. So basically, we still have the pooling or the kernel. After the kernel, we still have the output here. And with the kernel, with the after kernel output, we're going to pick the top 2 numbers. We're going to pick the top 2 numbers and throw out all the other numbers. So basically, max pooling is a specific case of key max pooling with key equal to 1. Okay. And dilation, I think that's the last concept. If it's not, don't judge me. I think yes, that's the last concept here, dilation. So another way, aside from the stride, aside from pooling, that's another way to do the compress. So dilation basically is another way of compressing data, but actually it doesn't make sense here, but I want to introduce it because it makes some kind of sense for the image. So if dilation equal to k, that means we're going to skip every k rows of the input. For example, just like a stride, actually it's pretty much like a stride. So dilation equal to 2, that means after the kernel, after we actually finish the kernel, finish the filter or the kernel, or try to find the pattern, we are going to skip the second, third, fourth, and sixth row. So we're gonna pick this one and we jump to the next one and we jump to the next one. So we're gonna skip every second row. Okay, so we're gonna skip every second row, fourth row, and sixth row. In that way, you know, we can have a smaller kind of like a, you know, 1, 2, 3, because 1, 2, 3 here, right? So it could be 3 left over as here, or fourth one, but he didn't actually write a little bit more. So by skipping every case row here, you can also have a smaller sentence. But just like a stride, this doesn't really make sense because you try to skip that word, this set of words, this set of words. Okay. Whew, okay, so that's basically all the concept for the CNN, for the CNN over here. Okay, and I'm gonna introduce a little bit more kind of advanced like research on the thing and try to actually tell you how the architecture of this thing is gonna look like. Okay, so Yoon Kim, which is, I think he's a PhD in computer science from Harvard University, and he's about to graduate in 2021. He already got a position in as assistant professor in the in MIT computer science department over there. Okay, so this is a paper by him in 2014 as one of his like job candidate paper. So we're going to use this to demonstrate how CNN works. Okay, so the paper name is going to Convolutional Neural Network for Sentence Classification. Okay, it's actually published right here, which is a super big journal for NLP. So the goal is actually try to classify the sentences. So basically, he collected a bunch of like a movie review or comments from Rotten Tomato website, and he tried to classify whether those kind of reviews or the comments are positive or negative using a CNN. So you can also apply CNN to other tasks, but mainly just classification, or you know, just classify the comments as subjective or objective, or classify some kind of questions. Is that about a person, location, or number? But he actually concentrated on this task right here. Those are just a side task from that. And what's amazing about his paper is that he actually used a single layer thing, so just one layer, so no more than that. So it's a really simple convolutional network, and he used this one convolutional layer and also pooling. So basically, the input is a word vectors, okay, word vectors with a dimension k, and the sentence is actually a concatenated vector. So basically, he concatenated all the sentence of all the words into one line or one row as the sentence right here, which is preceded or processed like a input here. So after that, he actually concatenated words a little bit more in different range, because you know, we try to loop through every single window over here. So he actually created every single window himself. So, and also it has some kind of convolution layer. So yeah, so filter is a vector. Yeah, so basically he has also a different kind of filters, different kind of like different kind of like a topic for each filter. So some of the topic could be like this one. It could be, I don't know, it could be about romantic, right? It could be some kind of romantic movies. So some other kind of like filters could be action movies over there. So we actually pick up different kind of like type of movies or different kind of like taste of the movies as a filter over there. Okay, so after he used a filter, he actually got this, right? Just like we mentioned previously. And he used a nonlinear transformation, which is a softmax function on top of that, just like this one here, and classify the sentence. So how that gonna work? So that's very abstract. Let's look into the graph and see how that works. So suppose we have the sentence, I like this movie very much. And suppose each word is a 5-dimension embedding, okay? So he used 3 different type of filters, which has 3 different size. A filter with size 2, 3, and 4, okay? So those 2 are filtered with size 2. Those are 3, and those are 4, okay? So in total 6 filters. So basically he loops through every 2 words here using those 2 filters, and he loops through every 3 words here using this filter. So this is just like an n-gram. This is very similar to the n-gram. So basically, am I actually looking every 2 words or every 3 words or every 4 words? He actually use, try to expand the n-gram as large as they can. So after the filter, he actually generates, different kind of channels here. So for this one here, it should be 1, 2, 3, 4, 5, 6, because we have 1, 2, 3, 4, 5, 6, 7. So 7 minus 7 minus 2 plus 1 should be 6, right? Just like we talked about previously, 6 here. So that's why it's 2. Okay, 7 minus 2 plus 1 equal to 6. And this one should be 5, and that one should be 5, and that one should be 4 and 4. Okay, so basically he didn't actually use any padding. He just say, keep actually going, looping through all these kind of windows over there. So after he used the filter, and next step, he actually used some kind of pooling and try to like max pooling actually. So he used some kind of max pooling and finds the most specific or largest or the most attractive pattern of each of the output here. So here it should be 1, which is this one here. And here, 1, 2, 3, 4, you just pick the largest one, it should be 1 here. And concave them together. And concave them together, you got, a new output here. Okay. And for this one, again, max pooling this one, max pooling that one, max pooling this one, max pooling this one. Okay. So we got another layer, which is not a convolutional layer. It's actually the output from the max pooling. The next step is we're going to concave them together. We're going to concatenate it. All these kind of like words or the output words going to be concatenated into this. And we apply a softmax function on this to classify whether it's positive or negative. Positive or negative. Okay. So as you can see, thinning actually breaks the whole sentence into different subparts here. So basically, I try to see, what these subparts represent? What that subparts represent? What these subparts represent? And I combine all the subparts together, what does this sentence actually represent as a whole? Okay. So basically, that's how thinning works. Any question with respect to this graph right here?
I have a question regarding the, in the paper it says it is using both pre-trained vectors as well as the task specific vectors. I don't quite understand at that part. Do you have any?
That's a very tricky way. Yeah. That's a good question. That's a very tricky way. So basically, he tried to do the comparison. He used some kind of pre-trained vectors for each kind of single word here. So pre-trained vector basically means, this one is trained. It's not 5. It may be like 16 or 17, right? So basically, he tried to use some kind of pre-trained vector embeddings to represent these words and actually do the classification and see how that works. Or I could just use my own kind of vector. I just name it. It should be 5. I just think it should be 5. Now I do my own kind of training and see how that works. At the end, he actually does a comparison between the two and say which one performs better. It turns out there isn't like huge difference between actually, the two data set he actually combined together. Yeah, so basically let's start from here. So it depends on whether you want to use your kind of like embeddings, like you want to actually start your own embedding, or you want to actually, use some kind of pre-trained word embeddings from online, or, Word2Vec or Globe, like we mentioned previously. So he more like he used a treatment group, he used a control group, then he actually compared those two and see which one performs better.
Okay, I thought the darker one was like using the pre-trained vectors, and the lighter, ones are using the self-defined ones. Yeah.
Right. Yeah.
Cool. Thanks.
Yeah. So yeah, basically he just combined those two together. But yeah, right. Okay. So that's this part. Yeah.
Yeah, I have another question. Since I'm not very familiar with word embedding method, so I look at this dimension equals to 5. So I was thinking, so if I extend this dimension maybe more than 5, will it improve the performance?
It depends. It really depends. Because because sometimes, you know, for long kind of words, for example, suppose we have encyclopedia, that kind of long words, you're probably going to represent, if you want to actually represent it with a long kind of like a matrix or long dimension over there, it's going to make sense. But since you want to keep every single word with the same kind of dimension, right? So for example, if you were going to represent the I using like a 20 dimension over there, probably there's going to be some kind of sparse component inside the matrix. So if it's too sparse, then when you try to learn this kind of word, it could generate some kind of negative or side effect in the process. Does that make sense?
So 5 is an ideal dimension for this.
Not really, not really. So basically what I do here is actually, I 99% of the time, I just use pre-trained word vectors. So they already define what kind of like dimension they have over there. For example, I think, I can't remember, globe, I think it's 14, or for others, it could be like a 25 or even a little bit more. So I just use their dimensions. Actually, I never define my own dimension over there.
Oh, got it.
Yeah.
Thank you.
Yeah. Yeah, but that's a good question. You could train your own embedding using your own kind of like 5 and redo this whole kind of process and see how that works with just like, you know, yeah, that's basically what I mean. Suppose we don't use this. We don't use the pre-train and just use this one. You know, it would be actually very good to see whether those kind of performs better than the pre-train or not. Yeah, okay, that's this part here. So model comparison. So let's compare different kind of models we learned previously. So we learned a bag of words or bag of vectors. It's actually surprisingly good because for the simple classification problems, especially if we actually use the ReLU as you know, kind of like classification or the hidden layer over there. So it performs really good for the simple classification. So as Michael, as Chris Mining, which is the lecturer of this course, he suggests like if you try to do a text classification or sentence classification, this is a baseline you should use, or the starting point you should use. Okay, or you could also use a word window, but it's good for a single word classification, not actually for you know, a sentence, because you know it doesn't really have the word context over there. CNN here is actually good for classification. So sometimes they need 0 paddings or for shorter phrases, but it's hard to interpret. But if interpretation is not your first priority, then you can use it. And it's easy to penalize on GRUs. So what does that mean? So basically, previously, when we talk about the filter, it's a pattern finder, right? So same kind of filter, same kind of weight can be shared with the whole data set here, right? It can actually go here to next one to the next one. So it's kind of like a parallel to different kinds of component over there. Suppose you have 3 filters, you could actually use 3 different clusters on the GRU to do the 3 pattern finding at the same time. Okay, so that's basically what it parallels the GRU means. So basically you can actually do the pattern finding for multiple filters at the same time. So that's a specific or the really kind of like, you know, time kind of like cost effective advantage of saying those over there. So that's also a disadvantage for RNN because it's not parallelized on GRUs, or it cannot actually perform in the parallel way because RNN, every single word afterwards or the next word actually depend on the previous word, right? So basically you have to know the previous word, then you predict the next word. So you cannot actually do the parallel way. So it's cognitively possible because they're reading from left to right, but it's not best for classification. Yeah, it's not best for classification. If we just use the last account like, you know, gate or the hidden layer or last state. So it's actually much slower than CNN because it's actually is reading from left to right. It doesn't actually read every single word in a parallel way. So it's good for sequence tagging and classification, not very good. It's just good for classification, but it's going to be great for language model, just like we actually learned previously for the question answering or, you know, try to predict the next word language models, sequence to sequence. And it's going to be, it performs pretty well with attention mechanisms. So in summary, if you try to do a text classification or more complicated version, go for CNN. And if you try to do sequence-to-sequence or language model, go to RNN. So that's the difference between the two. And this one is 5 times, based on my experience, it's actually 5 times more like faster. Using the same actual data set, it's actually 5 times faster than RNN here. Okay, for the same kind of like task book there. Okay. So next part is about the combination of the two. It's about the combination of the RNN and the CNN. So for the CNN, some people actually argue, can we actually use some kind of concept from RNN to CNN to actually improve the performance? The answer is yes. So one of the stuff we can do is that the gate units. Okay, so the gate units, LSTM and GRUs is actually a general idea. It can be actually used in many different kind of places. So the core idea is actually the vertical gate units is to sum the candidate update with the shortest connection or the shortcut. So for example, suppose this is a CNN network we have. Suppose this is one layer, and this is a convolutional layer, that's another convolutional layer, and between them we have nonlinear transformation, which is the ReLU. And suppose we have the one nation gradient problem, and we forgot about the previous layer. We can just skip the convolutional layer and add X as the end as the output over here. Okay, so this is called a residual block. So basically, we just skip the layers in the middle and we add them on top of the output of the layer. So basically, we are combining the two perspectives, by the summation. We are combining the convolution output, but also the output itself, X here. Okay, but when you do that, make sure you actually check the dimension, because X may have different dimensions than Fx. So when you add them up, you have to make sure they have the same dimensions. So you may need to pad X a little bit before you add them, or skip those kind of gates or the convolutional layers here. The second one is called hybrid block. Hybrid block is very similar to ResNet or residual block here. The difference between that is we don't do simple summation. We actually add some kind of weighted average. We actually do a weighted average by using some kind of gate right here. So we still skip the convolutional layer. We add it at the end of the convolutional layer, but we use some kind of gate to decide how much of X, how much of Fx we are going to take for the final result over here. Okay, so that's a hybrid block. To be honest, I haven't tried both, so I don't know which one performs better. But most of the time, according to the paper I read, most of the people actually use like ResNet a little bit more. I guess it's more simple than this one here, because for that one you have to tune your own gate by choosing different hyperparameters. It's gonna cost a little bit more kind of thinking. So that's this part. Last, I guess that's the last. Yeah, it should be the last. Yeah. The last most important concept is called batch normalization. I'm pretty sure a lot of you guys have heard about this many times. So batch normalization is try to transform the convolutional output of the batch by scaling the activation output to have zero mean and unit variance. So for example, first kind of question I want to ask here for you guys is, what is a batch? Anyone? What is a batch? Or the question could be, is a batch equal to the whole sample?
Using only part of the samples.
Yes, exactly. You only use a part of a sample to add input here. So basically, when you actually feed the neural network, you just use a single batch or just a little batch over there. Okay, then you redo this whole neural network using the second batch, third batch, so on and so forth. Okay, so that's a batch. So basically, the batch normalization means for between each kind of like output layer, especially convolution output layer, we actually do a normalization. So this is actually Z transform a statistic, just like we learned previously, X minus the mean divided by the standard deviation. Okay, it's updated per batch. So the fluctuation actually doesn't affect the thing that much. So what does that mean? So Okay, think about this as a neural network, the convolutional neural network we have. And why we actually adding this one here? Why are we adding the batch normalization after each convolutional neural network right here? That is because after the convolutional neural network, convolutional layer here, you could have like a sample which has been transformed. It could have a lot of noise over there. It could have a lot of or pretty high variance or pretty low mean over there. Okay, so if that's the case, that means, oh, I actually get a new data set after the convolutional layer, then I have to if we don't have the batch, I have to relearn this kind of pattern in the next layer. And for this one, I got another new data set which has really high variance and really low mean. I have to learn that myself using the next layer. But if we normalize everything using the same mean and same kind of variance, that means we don't actually learn new distribution. We actually have the same kind of distribution all over the time, which is gonna save a lot of time, but also a lot of efforts, by reducing the noise of the output from the previous layer. Okay, so that's batch normalization. So using the batch normalization make model much less sensitive to parameter initialization. Okay, because suppose this is the first layer. If you initialize with a really bad number, then it's going to generate a huge impact on this one. But if you normalize it, the impact could be mitigated a little bit. Okay, so since the output are automatically rescaled, so it also tends to make tuning of the learning rate simpler. Because if you normalize the batch, that means all the data are actually within the same kind of range of variance or same kind of range of the mean over there. That means you now, when you do the stochastic gradient descent to do a back propagation, you can jump a further step, a large step than previously. Because previously it's very noisy, so you have to do a little bit of step down to the hill. But now, since I know, everything's, is within a specific boundaries or a range, I can actually do a little bit more. We're using a larger learning rate to find the local minimum of the loss function over there. Okay, so that's why the learning rate tuning is going to be simpler than before. So now the choice is kind of certain. Previously, the choices could be anywhere. Okay, so batch normalization stems from the probability that the data may not be normalized between layers. So, but the problem appear in the intermediate layers, especially this one here. Okay, because of distribution of the activation, it's constantly changing during training. Okay, so every output is a new output. So if you don't actually do normalization, it's going to give you a new output. So the distribution of the activation is constantly changing during training. This actually slows down the training process because each layer must learn to adapt themselves to a new distribution every single training step. And this problem is called the internal covariance shift. Okay, so basically this kind of unnormalized distribution you have to learn for every single layer is called internal covariance shift. And that's why we are actually trying to use batch normalization. Basically, just like this one here, we just normalize this small batch by its mean and its variance. So make sure it has a unit, it has 0 mean and the unit variance over here. Okay. So you could also think about that as like regularization. So batch normalization can have a little regularization effect, but don't actually use it for regularization. So the regularization is more like a side effect it brings itself. Okay. So each batch is actually scaled by the mean and variance computed on just a specific batch. But just like we talked about previously, this batch doesn't equal to the whole sample, right? So this mean and variance could be biased. It could be biased. So this mean and variance could be a little bit far away from the true mean and variance of the whole kind of data set. So this add a little bit of noise to the activation for each kind of in each like a batch when you do the training, thus to the activation function of the hidden layer, so that each hidden layer doesn't actually rely on the previous hidden layer that much. That means this kind of hidden layer, this whole bunch of hidden layer doesn't really align with this small batch so precisely. It doesn't really perfectly fit the small batch. So if we do the normalization, that means we're going to learn the new kind of variance and means. That means we're trying to avoiding this kind of overfitting problem a little bit, because this is not the true variance and true means. Okay, so we are not getting close to true means and true variance. So we are not getting that close to the training data set. So we are not actually doing overfitting. So that has a slight regularization effect. Okay. So any question with the batch normalization here?
Hi, actually, I have a question regarding the batch. So
yes.
if you go to the architecture here, I want to know
the batch. Okay.
The architecture. For example, the entire training data has 200 examples, and your batch size is 50. So do you mean that we fit, like we just feed the model, we just feed 50 data points into the model? Is that
exactly
what the batch means?
So along with batch, I think probably you said you heard about this, or someone else heard about a pouch. It's another concept along with the batch. So basically, what we do here is we randomly select 50. We actually divide the data set into several different 4 different 50 batches. We feed each batch into the neural network. We find the parameters, the weight. Then we feed the next batch into the neural network and retune the weight. Then we feed the next batch until we feed all the batch. And after you feeding all the batch, so you loop through all the batches, the epoch is going to be 1.
Okay.
The epoch is going to be 1. Yeah.
The thing is that I also think of the stochastic gradient descent. That is when we also choose a batch of data and calculate and use that to calculate to backprop. So I wonder that when we use both, when we use backprop, we use a batch of data to backprop. When we use batch normalization, are they going to be the same batch?
No, it's not going to be the same batch. So the batch you use for the convolutional neural network is independent of the stochastic gradient descent batch. You can think about if you use a batch of 50 and use the stochastic gradient descent, it's going to be a nested batch for the back propagation. It's going to be inside the 50. I select another kind of mini batch over there.
Oh, okay, I see.
Yeah, but you can select other optimizer. So SGD is called optimizer. You can select Atom, or you can select Atom 2. So it's going to be different kind of like optimizers over there. But if you select different optimizer, but all the optimizers is going to be based on the 50 samples you actually put into the neural network.
Okay, so to summarize, one epoch is actually calculating one batch during the training.
No, one epoch means you loop through all the batches.
Oh, okay.
If you loop through all the batches, that's called 1. If you loop through second time of all the batches, it's called 2.
Okay, I see. Just partition the data into several batches and feed them each to the model.
Yeah, feed them sequentially. Each after so first batch, we loop through all the model, all the neural network. We find the vector for the weight. Then we feed the second batch. Then we updating this kind of like weight. We keep updating. So suppose we use all the batch, we finish 1 epoch, right? So we got a weight, and we don't stop over there. We do a second time of looping through all the batches, and we do a third time looping through all the batches. Okay.
Yeah. It feels like go ahead.
No, you go ahead. I actually finished my sentence right here. Yeah.
It feels like an ensembling method, but with normalization technique. Yeah, I think I got it now. Thank you.
Yeah. So batch is different from epoch. Okay. Epoch is not batch. Epoch means as long as you loop through all the data set you have, it's counted as 1. So it actually refers to 1 cycle through the full training data set. And batch is just a way you actually train the convolutional neural network, because if you feed all the data set into a neural network, it's going to be super slow. So why not just divide them into separate batches and train them separately? And then we actually do a sequential learning based on the previous batch and then try to find the best parameter we can find. But if you
or I thought
sequentially
parallelly training the 50 batch, training every batch.
No, we train every batch, but we have the batch 1, 2, 3, 4. By that I mean, you label all the batches over there and you feed them sequentially. So you feed the batch 1 into the neural network, then you feed the batch 2, you feed the batch 3, 4, 5, 6, 7, so on and so forth.
Okay. If we have enough time, I just want to do we have enough time so that I can ask?
Yeah. Go ahead. Yeah.
Okay. I was thinking, like, for batch norm, how do you learn from previous batch norm? Do you actually how do you learn from previous batch normalization result? How do you learn from the first batch when you are feeding
that's different. Sorry to actually make it confused. So what I mean previously is weights, like the weight, the parameter you generated on the first batch will be updated by using the second batch.
Oh yeah, that
now
one.
The batch normalization. Yeah, that's like the weighting or the back propagation to actually updating the weights is sequential, not the batch normalization. Yeah.
So for each batch, we train it parallelly, and then we kind of maybe average the final result. Is that the approach?
You can do it that way. You can just train each batch like parallelly, like in a parallel way, and just aggregate all the batch. But I think TensorFlow and PyTorch or the traditional network doesn't really do that. So basically, train each batch. Suppose we finish training the first batch, we got a W over there, right? So we put that aside, but we are going to keep that for the initial W as the next batch training. So we're going to updating the W from the first batch, and we get second. Yeah, so that's a sequential way.
Oh, yeah, I now get what is sequential.
Yeah, that's how sequentially this works. I mean, you could do it that way, but I never tried that way. I think that should make sense, but the convolutional or the conventional neural network actually doesn't do that way. It's going to do it in the sequential way. Yeah.
God, that really helps. Thank you.
Yeah. But batch normalization is not like sequentially. Which, like when we talk about batch normalization, it's within this batch. So we do the normalization. Yes.
Hey Daniel, it's I have a question regarding the bench normalization.
Sure.
I'm confused. Like how do you get the average mu and the standard deviation sigma?
So because you have each batch is a data set, right?
Mm-hmm.
So each batch is a data set. So basically, when you feed the batch into a model, it will actually have the mean and variance itself. It could generate those kind of two parameters. Yeah. Right.
So that's going to be unique for each batch, right?
It's gonna be, you're gonna have a new mean and variance after each layer, actually. So for example, if you look at this graph here, you're gonna have like a mean 1 and sigma 1 here before you actually feed into the neural network, right? But after you feed into a neural network, the distribution could change. Then now you have mean 2 and variance of 2.
So that's all. This is only specific to that specific batch for now.
Yes, specific batch. Exactly. Yeah,
okay.
That's basically batch you feed into the network. Yes,
so
exactly.
For the next training time, you have a second batch, and the mean and sigma will be different.
Yeah, it will be different. Yeah, basically you train different batch and you find different kind of like a mean and variances over there.
So if this is the case, in the prediction time, how do you come up with the mean and the sigma?
So when the batch normalization, after you finish the batch normalization, after you finish those kind of the entire network using, suppose this is batch 1, right? Then you're gonna have a W, right? And you do the second batch, and you're gonna repeat this, you're gonna have another W. So basically in the first batch, the normalization, the batch normalization is already embedded into back propagation. So it's used for finding this W here.
I see.
And in the second batch normalization is also in the back propagation. You also find a second W here.
So you already find only existing in the training time.
Yeah, it only exists in the training network. Yes.
So when you're in the position to do the prediction, you just use a W. There's no B anymore.
Yeah, so there's like, it doesn't make sense if you do the batch normalization for the test data set, right?
Mm-hmm.
I mean, think about it, because the way you try to do a batch normalization for a training network is try to reduce the noise and try to actually make it learn faster. But I mean, I don't know. I never done that for the prediction.
So basically, in the testing, you only have one record. It's very possible you only have one record. You don't gonna have a batch. It's very possible like that. So you don't even have a mean and sigma. That's
it could have just predicted one sample, right?
Yeah.
It could be right. But if you normalize the test data set, basically that means you already manipulated the data set. Then that prediction is not going to be precise. Basically, we don't actually, so when we do the training and test data set, we don't actually, I mean, pretty much of you already know, we don't actually touch the test data set at all. We don't actually do any, kind of like modification on that. Yeah, very good discussion. Yeah, thanks.
Yeah, thank you.
Any other questions right here? Okay, I guess that's everything. So there's here at least a lot of benefits of batch normalization. So sometimes if you actually interview for a machine learning engineer position, they will actually ask this kind of question. What is batch normalization? How you actually use batch normalization and why do you use it? So there's so many different kind of benefits right here, but the three kind of most important benefits. One is that the network is going to train faster, right? Because you normalize them, so you don't have that much noise. Second is like you can actually give it a higher learning rate, because gradient descent usually requires small learning rates. But as the network getting deeper, this gradient gets smaller during backpropagation, so it requires more iteration. But the batch normalization actually allows you to use a learning rates, because you don't have that much noise anymore. So you actually increase the speed at which backpropagation is going to do. And the last one, just like that, it actually provides a little bit of regularization, but don't answer the question like this. Don't just say, oh, I use it for regularization. No, it's actually not used for regularization. It just provides some kind of side effect which is not intended for regularization, just like I mentioned previously. Because we have the noisy mean and variance as we actually mentioned previously. So those are some kind of like advanced like technology or some advanced neural networks, which is not going to be. I don't think we're going to touch this for the assignment. So I actually listed in my kind of notebook here. So for you guys to actually give it a read. But other than that, that's basically the theoretical part of the convolutional neural network. So any questions so far? Let's just pause here for a second. If you guys want to discuss a little bit more on, the theoretical foundation of neural network, that's fine. Okay, so now I'm going to show you how to do the convolutional neural network using TensorFlow. It's super simple. It's going to be very simple. It's not that hard actually. So just like I mentioned previously, the convolutional neural network is actually mainly used for image or text classification. So that's the main task of the convolutional neural network. And why we actually use that for text classification is because it was built in that way. The architecture decides actually determining that it can only be used for the classification or mainly used for classification. So I'm going to pause where I'm going to stop sharing my screen here. I'm going to share how we actually use TensorFlow to do the convolutional neural network. So. Okay, I'm gonna share my screen here. Yes. Okay, so I'm gonna just show you really quickly a really simple, kind of really simple like a way to do the convolutional neural network using TensorFlow 2.0. You can use it in Google Colab because it was built in function over there, so you don't have to actually spend a lot of time installing, TensorFlow on your computer. So that's how I actually did over there. So first, if you try to use TensorFlow, you have to import TensorFlow as TF or as the any name you want. So that's how you actually start using TensorFlow. So I actually import NumPy and Matplot because I'm gonna actually show the difference between the training accuracy and the test accuracy later. And this is a key kind of like a part. So basically this line contains every single kind of concept we learn during a theoretical foundation. I know it's kind of overwhelming, but that's why, as you can see, that's why I actually talk about the pooling, normalization, dropout, dense layer, or whether 2D or 1D here. So basically that matters when you actually use the TensorFlow to do the CNN here. So I actually import the input because the input basically means the input layer. Convolutional 2D basically means I'm telling the system I'm going to use a 2D convolutional neural network. Dense layer basically just means the hidden layer other than the convolutional layer. Or it could be nonlinear transformation, just like a softmax or ReLU, just like that. Flatten basically means I'm going to concate, my kind of vectors into one row, right? Dropout, we talked about this previously. It's a regularization methodology you can use. Basically, you just drop some kind of neurons during the training and you don't use them anymore. Global max pooling, which you don't have to know, is actually try to pick the max number after you use the kernel. You can pick the max number of all the kernel units you have. We don't actually use that for NLP, so it's not that commonly used, so I don't actually go that deep. Max pooling, which we talked about previously, 2D, and batch normalization. Okay, so first step, we load the data. So data I'm going to use is already kind of embedded in the TensorFlow. Is called CIFAR10. I think basically all of you guys already know that. It's basically just a bunch of like a different kind of animals picture, which is really colorful, but the pixel or the resolution is really low here. I think it's 255 by 255 over there. Okay, so I import the data set from PF Coherence data set. So basically the TensorFlow deep learning or neural network architecture is based on top of the Coherence. Okay, it's based on top of the Coherence. So if you use a Coherence, it's pretty much the same kind of command, except for really tiny difference over there. Okay, so if you are familiar with Coherence, then when you switch to TensorFlow, it doesn't really affect your functionality over there. Okay, so I actually just split the data set into training and test the data set by using a load data function over there. Then I normalize the data set a little bit because the data set has 255 like pixels, I guess, for each kind of unit over there, data points. Then after that, I actually flatten the training data set and test the data set into one row, or you can think about one column. Because as we mentioned previously, what we do is a classification problem, right? So at the end, we're going to have a bunch of numbers which should have one dimension, or one by n, or n by 1, within which each number going to indicate the possibility that this image belongs to the specific class. Okay, so as you can see there, the training data set shape is a 5,000 by 32 by 32 by 3. Because it's image, so we have RGB 3 channels over here, red, green, blue 3 channels here. So that's a third dimension. And 32 by 32 is just like the height and the width of the image over there. So the training data set is 5,000 as well. Okay. So yes, number of the class is 10. The number of the class is 10 here. Okay. So let's start building the neural network. So the first step is actually the input. Okay, is the input. So this is just one way to building the neural network. There's another way, but this is the most common way to build the neural network right here. So I'll give it a name called I and input. And in the input, you have to specify the shape of your training data set. More specifically, you have to specify the shape of the first kind of data set, which is 32, first kind of sample, which is 32 by 32 by 3 over here. Okay, so we don't need that number. We don't need a 50,000 or 5,000 like as an input here. So keep that in mind, because when you phase the batch or the entire data set, so I don't actually use any batch here, by the way. When you phase the data set into the neural network, you already know how many samples you have. You don't have to specify that anymore. What it asks for is what is the other dimensions of the training data set? What's the width, what's the height, what's the RGB channel? Okay, so basically that is 32 by 32 by 3 here. Okay, so that's the input. Of course, there's the other kind of arguments over there, which I'll leave it to you. You can just explore yourself by searching this in the TensorFlow's official website. Okay, so the second step is after the input, I'm going to actually do a convolutional layer. Okay, so convolutional 2D, and the kernel size, or the number of the kernels. So if we just switch to this one, see here, convolutional 2D. The first kind of like argument is kernels. Basically specify how many kernels, how many filters do you want to use in this way. So for this one here, so yeah, the dimensionality of the output space, or how many kernels you want to use, how many channels you want to have, or how many feature maps you want to have, is actually the same. So I want 32 here, and 32 channels. And also the second argument here, so let's go back to in here, is actually the kernel size. Okay, so I choose 3 by 3 kernel size or filter size. And after that, I'm going to do a nonlinear transformation, which is activation, which is remove. And do you want to use a padding? For sure. If you want to use a padding, okay, you can just specify the padding. You can specify the same, full, or valid. And most importantly, don't forget the bracket, including I after that. That basically means you're feeding the output into feeding the input into the next layer X. Okay, don't forget about this. So we finish that layer. Next part, we're going to do a batch normalization. You don't have to specify anything, but of course you can specify some kind of like argument right here, but I didn't. So if you don't specify anything, basically it's going to figure out the mean and variance of the batch itself after the convolutional 2D layer. And don't forget X on the previous layer. Okay, so after that, I'm going to do the same. I'm going to batch normalization again. After that, I'm going to do a max pooling 2D. Okay, I'm going to do a max pooling 2D. So in the max pooling here, now it's called max pool, but the time when I use it is called max pooling. So make sure you actually follow the latest command over here. It's the first argument here is the pool size. So second argument is stride. Do you want to use a stride or not? The last one is padding, the padding. So as you can see, this is pretty common on the layers. You can use them all together, or you can just use one of them. So what I do here is I don't use a padding because I used a padding previously. So I just use 2 by 2. Okay, 2 by 2, which is the polling box size 2 by 2. Okay, so after that, I do another convolutional 2D. By this time, I'm going to increase the feature map. I'm going to increase the filter. Just like I mentioned previously, the image has been compressed, right? But I want to increase the channel, number of the channels to make it long triangle rectangle over there. Okay, so now I change to 64, but the kernel size doesn't change. Everything is else. Everything is else. Don't forget X after each one. Okay, and batch normalization, 64 feature map again. After that, I'm going to do a max pooling, right? And next part, I'm going to change a little bit. Now instead of 64, what about 128 feature maps or 128 weights or channels? So everything is the same. So after that, I'm gonna do a max pooling. And this is called stage 1. Okay, that's a convolutional blocks. This is called a convolutional blocks. So this part is called a convolutional blocks. So convolutional blocks basically contains the padding, pooling, or stride. So that's is called a one block. So basically I just use 3 blocks here, convolutional blocks construct the first stage. Second stage is a classification stage. So first, you have to flatten the output from the first stage because the default dimension is a flattened or the 1/n matrix for second stage. Okay, so I flatten that. Second, I'm going to use some kind of regularization parameters. I'm going to randomly drop out 20% of the output from previous layer. Then I'm going to use a dense layer. And in the dense layer here, I'm going to actually generate a 1,204 output. So this is how many output you want to generate. I want to generate those numbers. This is just random number, I pick it up. Activation function is a reloop. And I use the X from the previous dropout layer. Next, I'm going to drop out again. Next, which is last layer, I'm going to actually use a K, which is the class 10, because I want to generate 10. So dense layer, the first output here, the first argument should be how many output you want to generate after the dense layer. So here, because I try to classify that into 10 classes, so it should be 10. Okay. So the activation function is a softmax because it's classification, right? So I use the X from the previous layer. The next part is I'm gonna actually put that into the architecture or the architecture function, which is called model. So this step does basically just compress what you did in the previous first stage, second stage, and then you just compress that into a model. So that basically is a model container. And next, you're going to compile the model, but telling the model 3 main components. First, what is the optimizer, or what is the backpropagation algorithm? I choose Atom, but you can use SGD. Next, I'm going to do a loss function. So what is a loss function? Because this is like, this is like a, discrete classification problem right here, right? So I'm going to use a sparse category called cross entropy. Okay. And what matrix are you want to use for evaluating this function or this kind of like a neural network? I use the accuracy, but you can specify more than one. Okay. So as you can see here, I didn't use batch at first, and I stopped in the middle because it's huge. It doesn't actually works pretty well. So I think in the next part, I actually use a little bit of batch, but I'm going to specify, I'm going to tell you this first. So if you don't use a batch here, if you don't use a batch size here, so you're going to phase model X train and a Y train. So that's a training data set, but you can also specify the validation data, which is an X test and Y test. Basically, you have those two are the necessary argument you have to put here. And you can specify the APOC here. I think you can also specify the batch size here as well, or you can specify that before you actually starting the fading problem right here. But after that, this actually start to face the entire kind of models right here, entire model right here. So basically starting this whole kind of like APOC. So it looks like that. So basically, yes, it's going to tell you the first pouch is you have 50 pouches. So that basically you're going to loop through the entire data set 50 times. It's going to tell you, oh, I finished the first pouch and loss is this number and the accuracy is that number. So validation set or the tested data set loss is this, and tested data set accuracy is that. So as you can see, it's actually improving all the time until 50 over there. Okay. So at the end, I want to see how that performs between like a training data set and a validation or tested data set. So I use the plot function here, and R here refers to the model, right? R here refers to the model, which is the model fit here. So it has some built-in function, which is called history. History contains all the metrics you specified previously, which is or the loss or the accuracy. It contains both. Okay. So if you specify R history and you just specify loss, basically this means the training data set loss for each pouch over there. Okay, each pouch over there. And if you specify that as well loss, that means it's going to give you the loss for each pouch for the tested data set. So basically, I just plot that out. It's okay. That means each pouch should stop at about, it's a little bit like each pouch should stop at 40 or 30, it should be fine, but I use it a bit more. It looks okay. And you can also actually look at the accuracy. So again, use art history, specify the accuracy. This is a training data set accuracy. And if you specify the well accuracy here inside the history function, or it's actually a data set, so it's going to give you the test set or validation data set accuracy. And if you plot them, it's okay, just like previously, just like this graph right here. Okay. So next, I actually define my own kind of function, try to see the confusion matrix here. Basically, I try to see, which two labels are more easily to actually be confused with each other. So there are 10 labels here, 10 labels here. As you can see, we just ignored the diagonal here, but we have the high number here, which is 3 is more often confused with label 5. So what is 3? 0, 1, 2, 3, cat, 4, 5. Oh, so cat is more often confused with dog, which actually makes sense sometimes, because if the if the data set, if the picture looks like this, the neural network may classify as cat or dog, right? It's really hard to say. So I'm gonna randomly select one wrongly classified image and see what is the original label and what is the predicted label. So I select this random picture here, and the true label is frog, and the predicted label is bird, which actually makes sense because it looks like bird, but if you see it really kind of closely, it should be a frog right here. Okay. Another kind of function you can also use, which is model summary. So model summary gives you all the dimensionality you are looking for each hidden layer, for each layer. So for the first layer, it's going to tell you don't have any parameters because we haven't actually trained the data set. We don't have any parameter with the input for sure. As second layer, we have all the dimensions here, and we have number of parameters. So for each layer, you can have the number of parameters you have. At the end, it's going to tell you how many parameters you want to train here. As you can see, it's a huge number, even though I just use a batch of 35. Yeah, 32. I just use a batch of 32, but it's a huge number over there. And it's going to tell you the non-trainable parameters and the trainable parameters. Yeah, that's pretty much how you can use TensorFlow to use convolutional neural network. Any question here?
Hi, Daniel. Where did you define your batch size?
I just defined my own batch size. You can define what number you want, actually.
So you can I see the code over there?
Right here.
Oh, and then you put, okay, so you put into the...
Yeah, I just divided, see, I divided by the batch.
Okay.
Yeah.
So what's the train generator? What's the train generator?
Train generator. Oh, this one here. Basically, because I try to generate a small batch, so I use the train data generator to generate a small batch right here.
Oh, I see. Got it.
Yeah. But you don't have to do this. This is like, yeah, some kind of floppy way to do the batch. I think, let me double check. I think it should have some kind of batch size specification in the model fit right here. Let's see. PF, QRS. I think it's model fit right here. Model. Model. I think you can specify the
yeah, it's fine. So after you have the batch, you use a do loop to feed the batch that you generated.
Yeah, that's basically what I do. But I think there should be some kind of way you can do that.
Yeah, I think so too.
Yeah, that's basically what I do. I just put them one by one over there. Let me double check. Okay. Let's see. Model. Yeah, model fit right here. Compile, evaluate. Yeah, let me go back to this. I haven't trained in my notebook for a very long time, but I think you could. Yes, exactly. You can specify a batch size right here, unit function.
Okay, so you can save your code for not having.
Yeah. That's why I'm saying it's a floppy way. I think I just did like, before I know there's a batch size right here. Yeah.
All right.
Any other questions right here?
Oh, so this is the image example.
Yeah.
For the NLP, do we have similar example, or we can find it through the paper?
I don't think I have any example with NLP here, but in the assignment you should have that. So basically for NLP, it's not 2D, it's going to be 1D. But most of other stuff should be the same. I think it should all be the same, except it's not 2D, it's actually 1D now. Yeah.
Because in the image processing, we have the fixed input image size, right? But in the NLP, we have different lengths for each sentence.
Yeah, and basically, yeah, right.
So for that situation, I remember that when you introduce the paper, there's a max pooling or any pooling layer that they smartly extract only one feature out from the convolutional results that eventually concatenate into a final vector to do the classification. So I think I think they have some special architecture for doing that as well. Like
generally speaking, like you can see here, Conv1D has the same kind of like, argument as we have. For the max pooling 1D, I think it should be the same, but because I barely use 1D, but I'm not sure, so let's double check. Max pool 1D, yeah, it's actually the same.
Yeah, you connect max pool 1D right immediately after the
convolutional.
Convolutional 1D, and then should be good.
Yeah. So there's no, you actually remind me, Yunfei. So there's no kind of stride layer. So stride is embedded into pooling here. Okay. So if someone asks you, is there a stride layer? No, there's no such layer. It's just embedded into those kind of functions right here.
Yeah, you can specify strides over there.
Yeah, so stride is everywhere. It's embedded in the neural network. It's actually not isolated as one layer. Yeah.
I can try this later.
Yeah, I think it should be easier. It actually should be much more. It should be faster than just image, because image 2D has a lot of more parameters. But for 1D, it should be much less. Any other questions? You can also use PyTorch. I think PyTorch has a similar structure, but different kind of language over there, different kind of architecture. But generally speaking, the theory for both are the same. It's just like there's a tiny bit of difference between the two, how to actually construct the neural network. Because TensorFlow is by Google and PyTorch is by, I think is by Facebook, right? So basically, they have different ways to code the neural network, but the theory should be exactly the same.
Oh, one more question. Because when we construct the image convolutional network, we have the input layer, which is a fixed size, right? For the neural network, we cannot have the fixed input layer. So what does it gonna report any error? I'm not sure.
Oh, that's gonna be okay. For the input size, although you have different kind of like, the size for different kind of like sentence right here, but it's not gonna be the problem, because the problem gonna happen when you feed the input layer into the next layer, right? So that way you do that is try to make the padding. Try to pad them and make them has an equal length out there.
Really? Because I think in a picture, in the literature that you introduced before, that paper doesn't use any.
Oh, I see your problem. Okay, sorry. I thought it was like a different question. Yeah. So this. Oh yeah. That question you have to pad your sentence yourself. You have to make sure it's the equal length over there. So I don't think it's that hard. You have to find the maximum length of the sequence over there. Then you pad
so
every single.
You have to fix the input length.
Yeah, you have to fix the input length, make them equal. Yeah.
Okay, because I'm thinking like if we can just, I mean, like eventually they will use a max pool to get equal, like intermediate level of the vector over there. But I'm thinking it will be better.
But for the input, you still have to make them equal. Like they have to be the same size over there for sure.
Yeah. But what if they are not equal?
Pad the shortest one with 0. Just like we pad the image with, like zeros over there. Suppose, for example,
what will happen if we don't do the padding?
Because you have to multiply the input with the filter, right? So if you have a different kind of sentence over there, it's not going to be 3 by 4.
Oh, everything doesn't make sense then.
Yeah, it doesn't make sense anymore. So you have to have the same kind of length or embedding for each kind of word over there. But if you have less word for one sentence, then it's going to be a different kind of matrix, right?
I think it won't make any difficult or the problem in the calculation. It's just like if you don't have a fixed input, I think when you construct this architecture, they will report error because they expect your input layer to be fixed.
Yeah,
but actually, if you have different length, when they convert into different lengths of vectors after the convolutional layer, you still can use the max pool to only generate one output, regardless of the input length.
I think for the neural network, before you fit into the convolutional layer, you have to make sure they have the equal length for sure. The dimensionality for each kind of like single word over there should be the same. For each actual sequence over there, it has to be the same. Yeah. I think they have in the PyTorch notebook in the lecture, they actually do that for the sentence over there, which is, I don't think it's very hard. Just find the maximum sequence and pass on the actual sequence or actual
space.
Yeah,
it's not hard. I'm just thinking if it can do that without the padding. It leads to another question.
I hope so. I hope it can be, but I don't think so. Yeah.
Yeah. So it leads to another question. It's not about CNN. It's about RNN. So remember that the RNN, one of the benefit about RNN is we don't need to consider the length of the sentence, right? When we fit into the RNN architecture. So.
Oh, no. Don't interpret it that way. It's that it can be any length, but it doesn't say we don't have the same length for all the sequences over there.
So we still have the padding like when we fit into the RNN.
Yes. It can be any length. It's just that you can be any length of the sequence, but for all the sequence, like you put over there, it has to be the same.
But if that's the case, when you're padding them, you kind of having the trouble with the short-term memory as well, because if you're padding them with empty space, right, or space with them, and then they will learn from the previous information, but they will lost the memory when they go through all the the trailing space. So that's kind of a problem.
For one, if you pass them with 0 multiplied the weights is still 0. They don't learn from the pad zeros. So that's my question.
So you don't think it's going to affect the result?
No, it's not. I don't think it's actually not going to generate a problem, because when you pad it with 0 times the weight is going to be 0. So it's like a data neuron.
Okay.
Yeah.
It just costs more computation, right? It just because they have to go through the zeros.
Yes, it's like RNN thing is not that smart, so it cannot actually feel different kind of lenses over there. So sometimes you have to prepare the same lens for them to face them as an input.
Makes sense. All right, thank you, Daniel.
Yeah, that's a good question. It's not like we don't have to deal with the input for the RNN. It's like RNN can be length 2, 3, 4, but if you certain you're going to use the length 4, then make sure everything's length 4. Yeah.
So you have to pad in with the maximum sentence length.
Exactly. Yes. Any other questions? Yeah, that's definitely a lot of more work to do than this, because this one's like a perfect data set that you can use, because it's like unified data set, it's equal length, like it's everything the same. But if you don't have this kind of data set, you have your own data set which have different lengths, then you are going to have a bunch more cells on top of this kind of like a neural network, which is like a data pre-processing stage you have to do yourself for sure. Yeah. All right, if you don't have any problem, let's call it a day, and we can talk a little bit more later next week or in the WeChat group. And that's everything. Thank you guys for attending the lecture, and I hope to talk to you guys next week.
Thank you, Daniel, for the lecture.
Thank
you so much. Thank you all.
Thank you so much. It really helps.
Thank you so much.
Thank you.